So in the last video, we talked about how could we use the graph to help us figure out what the limit is. But using the graph every time or graphing every function to find the limit could get a little tedious. So there's got to be an easier way. And it turns out there's an algebraic way for us to figure out what the limit is. And all we really have to do if we have a function, and this works really well, especially for polynomials and rationals, is we just plug that value in and we see what the y value is going to be. So if we look at this one here, matched problem 5, they're asking us to find the limit as x approaches -2 for the quadratic x squared plus 5x. So to find out what that limit would be, we're going to substitute in -2. So that's going to give us a 4 minus 10, which is -6. Now I want to compare this to the graph. So I'm going to go to Desmos and graph this. So I've gone to Desmos. It's a really nice graphing calculator, and I've typed in the function x squared plus 5x. We want to know what's happening when we get close to -2. So here is our -2 down here. And if we were to, let me see if it'll let me move that point. Maybe not. So if we were to come in from that left-hand side, okay, you can see I'm moving along that graph, and I want to get close to x equals -2. So there I am. I'm close to -2, and at -2 from the left, you can see we're getting close to that -6. Now we can come in from the right side too, just following all those values. As x gets close to -2, we also see from the right that we're getting close to that y value of -6. So since the left hand and the right hand limits are giving us the same value, then we know that limit is equal to -6 also. It's the same thing we got when we substituted that in. So let's do a few more of those. Let's look at matched problem 6. In matched problem 6, we've got a few more functions here, and we can figure out what the limits are going to be. So let's say we substitute in a -1. We have a 4th degree polynomial. We want to know what is the limit as x approaches -1. For a polynomial, all we have to do is substitute in. So that's going to give me a 1 plus 2 plus 3, which is 6. In part B, substitute in. That's going to be the square root of 12 minus 6, which is the square root of 6. And then substitute in for C. We're going to have -2 squared over -2 squared plus 1, which is going to give us a 4/5. So we can use that same idea for polynomials, like in part A, rational functions as in part C, and even square root functions in part B. We can actually also use it for piecewise functions. We just have to figure out which piece do we need to use. So if we look at A is asking us to find the limit as x approaches 5 from the left of f of x. So from the left, I'm going to have to use this top piece because the domain to the left would be values less than 5. So if I substitute that 5 into the top piece, I'm going to get 13. So that limit would be 13. If I want 5 from the right, then that means I have to use that bottom piece, because that would be values greater than 5. Substitute in -5 plus 12. It's going to give us a 7. Now, because we know the left and the right hand limits, we also know what the limit is at 5. Notice they are different numbers, which means this limit does not exist. Now, if we were to look at f of 5, notice this function is not defined at 5 because I'm either strictly less than or strictly greater than 5. So we would say this does not exist either. So I want to do just a couple more of those. Looking over here, let's look at 56. And this is where you may want to Pause the video, try it, and then come back. So if we look at 56, we want to take the limit as x approaches -3. You've got to figure out which piece do I use. Well, -3 would fall in this domain. So I've got to use that top piece. So I'm going to have -3 over -3 plus 3. -3 over 0 does not exist. We know we can't divide by 0. So let's find the limit as x approaches +3. Well, as x approaches +3, we're going to use that second piece because +3 falls in that domain. Substituting in what we know, we're going to have +3 over 3 minus 3, which is a +3 over 0, which also does not exist. So the limit for this function does not exist at +3 or at -3. But let's look at part B. Part B is asking us the limit at 0. So to figure out the limit at 0, we're going to have to look at the limit as x approaches 0 from the left, and then the limit as x approaches 0 from the right. So if I come in from the left, I'm going to use that top piece. And I'm going to have 0 over 0 plus 3. So this is going to get really close to that y value of 0 from the left. To evaluate the limit as x approaches 0 from the right, we have to use that bottom piece. Substituting in, we're going to have 0 over 0 minus 3, which is still going to give me a 0. So what that means is that the limit as x approaches 0 of f of x does exist and is equal to 0. So now let's do a few more algebraic ones. Let's look at 29. We want to find the limit as x approaches 3 of 4x. All we have to do is substitute in the 3, and we're going to get 12. So what's happening to that graph, if we were to graph the function 4x, we're going to get a line. As we get close to x equals 3 from the left and from the right, all of those y values are approaching that value of 12. Let's do another one. Let's look at 32. Same thing. We want to know the limit as x approaches 5. Just substitute it in, and we're going to get 2. And then let's look at 36. Substitute in, and we are going to get 1. Okay, but sometimes when we substitute in, we may end up getting something like 0 over 0, and that is called an indeterminate form. There's actually other forms that are also indeterminate, but we'll talk about those later in the course. So when you have an indeterminate form, what that means typically is that you need to look at, does that function reduce in any way? So here's what you need to try. Try to factor, and then try to reduce. And once you factor and reduce, that usually is a rational expression. Once you factor and reduce that, then I want you to try the limit again. Most of the time, that's going to fix whatever the problem is. So let's look at matched problem 8. If we were to look at this, we take the limit as x approaches -3. So notice if we were to plug in a -3 right now, we would have -3 squared plus 4 times -3 plus 3 over -3 plus 3. And we're going to end up with 0 over 0. That is a key to let you know that you need to try to factor and reduce. So let's do that. If we were to factor, this factors in the x plus 3 times x plus 1. And do you see how those x plus 3's cancel? So that function is going to look like the function x plus 1 as long as we don't substitute in a -3. So now if we were to take that limit again, and we're going to plug it into x plus 1. We're going to have negative 3 plus 1, which is a negative 2. But there's no way we could have gotten the negative 2 algebraically without reducing that function. So always think about those 0 over zeros. If we look at matched problem B, if we plug a 4 in here, we're going to get 4 squared minus 16 over the absolute value of x minus 4. So we're going to get a 0 over 0 here also. Now, this means that this does reduce, but because we have that absolute value, I'm going to resort to looking at the graph for this function. So we're going to go back to, I'm going to use Desmos. So we have x squared minus 16 divided by the absolute value of x minus 4. So this is going to look like a linear function also. And we want to know what happens as x approaches 4. So I'm going to zoom out on this graph. Okay, so look at what's happening here. As I approach 4 from the left, notice my y values are getting really close to negative 8. It's actually undefined here at 4, but it's getting close to negative 8. But as I come in from the right, notice I'm getting really close to positive 8. So the limit as x approaches 4 of this function from the left was negative 8, but from the right was positive 8, which means that limit at 4 does not exist. So I want to examine this one just a little bit closer. So we are looking at the limit as x approaches 4 of x squared minus 16 over x minus 4 absolute value. So we've got to remember that definition of absolute value. We talked about it earlier. The absolute value of x is equal to positive x as long as x was greater than 0, or greater than or equal to 0, and negative x as long as x was less than 0. So what we're saying, right-hand side of the graph follows y equals x, left-hand side follows negative x. Now, if we were to look at that transformation, x minus 4, all that does is shift that graph to the right 4 units, which means it's going to look like x minus 4 when x is greater than or equal to 4, but it's going to look like the negative of that when x is less than 4. So if we were to look at left-hand and right-hand limits, approaching 4 from the left means I'm looking at this piece. So I'm taking the limit as x approaches 4 from the left of x squared minus 16 over the negative of x minus 4. And we know we're going to see something reduce. That factors in x plus 4, x minus 4, all over negative x minus 4. And you see those x minus 4's reduce. So we could take the limit as x approaches 4 from the left of x plus 4 over that negative 1. And now if we were to substitute in, we would have 4 plus 4 over negative 1, which is negative 8, which is the same thing we got when we did this by looking at the graph. Likewise, if we were to look at the limit as x approaches 4 from the right, we have to think about that piecewise function again. And as we come in from the right, then that function, absolute value of x minus 4, would look like this piece. And once again, we're going to see some reducing. So now if we take the limit as x approaches 4 from the right of x plus 4, we're going to get that positive 8 that we saw from the graph. So we're going to get the same results either way. This one is a little tricky to do algebraically because you've got to use that idea of how can I rewrite absolute value in terms of a piecewise function. But we could get the same answer algebraically or by using the graph. So just for fun, I want to do a couple more. Let's look at matched problem 9. In matched problem 9, we're asking for a few limits, and we're going to determine, can we find the limit, or is it an indeterminate form, and do we need to tweak before? If we look at that first one, if we were to substitute in a 3, we have 3 plus 1 over 3 plus 3, which is 4 over 6, which reduces to 2/3. So that limit we can find as is. There are no issues with that one. Not an indeterminate form. If we look at B and we substitute in the 3 here, notice the top is going to give us a 0 and the bottom gives us an 18. 0 divided by 18 is going to be equal to 0. So that one's fine as well. But if we look at C, now, if we try to substitute in 3, we are going to get that indeterminate form of 0 over 0. So that means that we need to try to factor and reduce. So if we try to factor this, top factors into x plus 3 times x minus 3. We can see those factors reduce. So we take the limit as x approaches 3 of x plus 3. And we're going to get 3 plus 3, which is 6 for our final answer. Just for fun, I want to do 1 or 2 more of those. Let's look at 59. 59 is asking us to find the limit at 0. So if we plug 0 in, we're going to have 0 minus 2 over 0 minus 0. This is going to be negative 2 over 0. That's undefined, so this limit does not exist. We can find the limit at 4. So this is going to be 4 minus 2 over 4 squared, which is 16, minus 2 times 4, which is 8. So we're going to get 1/4 there. But if we look at B, we're going to have 2 minus 2 over 4 minus 4, which is giving us that indeterminate form. Anytime you get that indeterminate form, you have to factor and reduce. So if we were to rewrite this, that denominator factors into x times x minus 2. And what you'll notice is those x minus 2's cancel. So we have 1 over x. And now we can plug that 2 in, and we're going to get 1/2 as that limit. Now, we could have maybe we saw in the beginning, this would already factor and reduce, and that is perfectly fine. You can go ahead and factor and reduce and then evaluate all of the limits. You're going to get the same answer either way. So if we were to use this 1 over x here for part A, we could take the limit as x approaches 0 of 1 over x. We will get the same answer. That one still has an issue because you can't divide by 0. So it still would be undefined or does not exist. Part C, we would still get the same answer if we take the limit as x approaches 4 of that reduced function, 1 over x. We will still get 1 over 4. So let's look at 61. So if we look at this one and we want to find a few limits, I'm going to go ahead and factor and reduce before I start. So that numerator factors into x minus 3 times x plus 2, and that's over x plus 2. Notice those x plus 2's reduce. So this function actually looks like the function x minus 3 as long as we don't plug in negative 2. At negative 2, we would have a hole in this function. So what if we want to find the limit? Well, this means we're taking the limit as x approaches negative 2 of that function x minus 3. And if we substitute in, we're going to get a negative 5. If we take the limit here as x approaches 3 of the function x minus 3, I'm using that reduced function again. We're going to get 3 minus 3, which is 0. And then if we take the limit as x approaches 0 for that function, we're going to get negative 3. So using that reduced function really makes it easier to find those computations. And it does eliminate, usually with a rational function, the issue that could happen with dividing by, or that indeterminate form 0 over 0.